सो इस वीडियो में हम लेक्चर्स 1 and 2 कवर करेंगे. टॉपिक्स लीनियर ODEs, order of an ODE, direction fields and isoclines, and we'll move on to the important part, solving ODEs, and we'll cover 3 types essentially: separable, homogeneous, and exact and closed forms. I also want to take this moment to briefly mention that the goal of this course and of all these videos is to be able to solve differential equations, and everything we do and study will be to be able to solve more and more differential equations of various types. So first things first, let's cover the order of an ODE. For the order of an ODE, you just check which is the highest derivative of y, which is the dependent function in the ODE. Let's look at an example. In this first example, we have the third derivative of y plus 4 times the square of the first derivative of y, which equals y. Here, because we are taking y's derivative with respect to the independent variable, y will be the dependent variable or the dependent function, and the highest derivative of y in this equation is the third derivative of y. So the order of this differential equation is 3. Similarly, you can find the order of the second example and of any other differential equation. The reason the order is important is because we've developed order specific methods to solve differential equations. So there are methods which work for first order differential equations and then methods which work for second order differential equations. And to use these, we must first identify what is the order of the differential equation. A linear ordinary differential equation is a type of ODE which is linear in y and every derivative of y. What this means is that there shouldn't be any terms like y squared or the square of the first derivative of y or y into the first derivative of y. None of those terms are allowed in a linear differential equation. You can see the general form of such an equation given here in the definition. So on this slide we've got some exercises for you, and I'll solve the first one. So if you look at all the terms, you can notice that 1 minus y squared is being multiplied with the second derivative of y. Now we can't have any products of y and or its derivatives with themselves. So this first equation is not linear. Let's also find the order of this first equation. So now once again look at all the terms and note which derivatives of y are present, and you'll notice that you have the zeroth derivative, which is y itself, and you have a term with the second derivative, and then you have a term with the fourth derivative of y. So of course the fourth derivative is the highest derivative of y present. There is no higher derivative present. So the order of this differential equation is 4. Similarly, you can check for linearity and find the order of the other 2 equations. And just a hint, be careful of which variable is the dependent variable and which variable is the independent variable.
So now let's talk about direction fields. So direction fields are basically just finding the slope of your function f of x, y at different points and then finding the vectors at all the points with corresponding slopes. Now when you trace these vectors, you get an approximate form of what your solution curve is going to look like. Now why this is essential is because sometimes the ODEs might not be solvable. So this might help us to analytically get a rough idea about the curve. Basically what you have to do is arrange the ODE so that you get dy by dx is equal to sum f of x and y, and then since dy by dx is that f of x and y, that becomes the slope, and then h of x of y becomes 1 comma f of xy, which is like the unit vector basically pointing in that direction. So let's talk about isoclines. An isocline for the first order ODE dy by dx equal to f of xy is the curve f of xy equal to c. Now you might ask, what's the essential need for an isocline? And I'd agree. But Basically, on isocline, all the direction fields are constant, that is, the vectors are pointing in the same direction. And sometimes it might not be easy to plot all the direction fields. So, what we do is plot various isoclines, and then on those isoclines we plot various different vectors, and by tracing those vectors we get a rough analytical curve. Again, this is only helpful for ODEs which aren't solvable properly. So, this is very useful for analytical purposes.
Another type of differential equation is called a separable differential equation. This is a first order differential equation which can be represented as a function of x which is independent of y plus a function of y which is independent of x multiplied by the first derivative of y. This is called separable because the x dependent terms and the y dependent terms have separated. And now you can simply integrate the whole equation with respect to x to get the solution. If you try it, you will get the integral of n of y with respect to y, that is integral of ny dy, equaling minus of the integral of mx dx because we have moved mx to the other side of the equation. So let's look at a couple of examples. First of all, first derivative of y plus 2 into x into y equaling x. Is this equation separable or not separable? Think about it, pause if you need to. The solution is move 2xy to the other side and then take x common. Then you can divide the whole equation by 1 minus 2y and you will get the first derivative of y divided by 1 minus 2y equaling x. Hence the y dependent terms and x dependent terms have been separated, and you can check mx is in this case minus x and ny is in this case 1 by 1 minus 2y. Now let's take a look at the other example. The first derivative of y minus 3y equaling e power x. Is this separable or not? Pause if you need to. And the answer is it is not separable. Nothing you do will make the y dependent terms be only the coefficient of the derivative of y. The y dependent terms will always be in addition. So you can't write this in terms of mx plus ny y1 equals 0.
Basically, let us just discuss the exercises. I discussed the first one and the rest 3 you all can do. It's basically J. So x cube sine y dash equal to 4.2. Let's just take dx on that side, x cube on that side, it becomes sine y. dy equal to 4.2 dx by x cube. Then you do a basic integral on both sides. You get minus cos y equal to 4.2 divided by 3x square with a minus sign plus c. So you can consume the minus in the constant and you get cos y equal to 4.2 divided by 3x square plus c. And basically you get cos y equal to 1.4 by x square plus c, and you can put y as a cos inverse of 1.2 by x square plus c. But now the important thing is you also have to pay attention to what happens when you're dividing by x square. Now this might not sound very intuitive to you at this point because this is not an initial value problem, so we can't break it into intervals and talk about uniqueness and exactness and all of that. That's a discussion for a later time. But all I can say is you just have to be careful, so pay close attention to when you divide by x square, x cube, divide by x basically, where it turns 0, and you will have to basically check it in the solution. So in this, it is going to infinity. Cos inverse of infinity is not defined, so you will have to do some manipulation at x cube, and that we will check. Anyway, cos inverse of y has a domain of -1 to 1, so the IVP will be set in such a way that this problem doesn't occur. But if it does occur, then we will have to keep close look on what you're doing, so please pay attention to that. And the rest 3 are basically similar, just pay attention to when you're dividing by what. And the fourth example is pretty nice, so do solve it.
Now we are going to look at another type of differential equation, the homogeneous differential equation. But before we can do that, we must look at homogeneous functions. So a function has some input variables, and a function is homogeneous if when you multiply all inputs by some non-zero number t, then the output or the value of the function becomes some power of t times what it previously was. So that is the definition of a homogeneous function, and that power of t, it must be an integer, and that power is called the function's degree. So let's take a look at a couple of examples. First up, f of x and y equals x square plus 24xy plus y square. So just substitute tx and ty instead of x and y, and you get tx whole square plus 24 into tx into ty plus ty whole square. Now you can take t squared common from each of these terms, and you are left with the original function. Hence, f of tx comma ty equals t squared into f of x comma y. So this function is homogeneous and its degree is 2. So try the next one yourself. F of x comma y equals x plus y into cos of y by x. Pause the video if you need to. The answer is it is homogeneous, because when you replace x and y by tx and ty, you can take t common, and inside cos ty by tx, the t cancels and you are left with y by x. So you get f of tx comma ty equaling t into f of x comma y. The function is homogeneous with degree 1. Let's look at the other examples. F of x comma y equals ln x squared into y. Pause if you need to. And the answer is it is not homogeneous. You can check, replace x by tx and y by ty, but you can see there is no way to take any power of t common from this and be left with f of x comma y. So this is not homogeneous. Let's try the last example. F of x comma y equals x into y squared plus x squared. Pause if you need to. Again replace x with tx, y by ty, and you can see from x into y squared you can take t power 3 common, but from x squared you can only take t power 2 common. So from the sum you can't take any power of t common and leave the rest as f x comma y. If you take t squared common, you will be left with t into x into y squared, and if you take t cubed common, you will be left with x squared by t. So you can't convert f of tx comma ty into t power d into f x comma y. So this is also not homogeneous. Now let's move on to homogeneous differential equations. A homogeneous differential equation or a homogeneous form is a first order differential equation in which the coefficient function of the first derivative of y and the other function which is added to this to make the differential equation, both these functions must be homogeneous functions of the same degree. Now homogeneous forms are useful because they can be very easily converted to a separable differential equation, which we already know how to solve. Now the trick to this conversion is to substitute y equal to vx. This is the definition of the new dependent variable v, y equal to vx. And we substitute this into the differential equation. Now we substitute y equal to vx in the differential equation, and we also take the derivative of this y equal to vx to get the derivative of y equals the derivative of v into x plus v. So we substitute this for the derivative of y in the differential equation, and now we don't have y in our differential equation. We only have v and x. Now let's simplify this a little further, and here is where the homogeneous nature of m and n comes into play. M of x comma xv, because m is homogeneous with some order d, can be written as x power d into m of 1 comma v. just like we did with f of tx comma ty equaling t power d into f of x comma y. This is the same thing. Similarly, we can write n of x comma xv as x power d into n of 1 comma v, and the d is same both for m and n by definition of a homogeneous differential equation. If they have different orders, then it is not a homogeneous form. Now we let x not equal to 0 and divide the whole equation by x power d. And now this is a separable differential equation. So you just take the derivative of v to one side of the equation, multiply the equation by dx, divide by x, and divide by m of 1 comma v plus v into n of 1 comma v. And there you go, you've separated the x dependent parts and the v dependent parts. Now you can just integrate, and once you're done integrating, you can substitute back v equal to y by x from the definition of v, and you'll get your answer in y and x. Now note that the method assumes that x is not equal to 0. So you might think that the solution is not valid at x equal to 0. But the thing is, by assuming x not equal to 0, all we are saying is that the solution is not guaranteed to satisfy x equal to 0, but that does not mean it cannot. The solution you get may still be valid at x equal to 0, but you will have to check that separately. This method does not guarantee that, because this method only guarantees that the solution will be valid for all values of x not equal to 0.
So basically, let us talk about exact ODEs. A first order ODE m of xy plus n of xy into y dash equal to 0 is exact if there exists some u equal to u of xy such that del u by del x is equal to m of xy and del u by del y equal to n of xy. And from MA108 knowledge, you know that du can be written as del u by del x into dx plus del u by del y into dy. And when you substitute it in the ODE, you can easily see that du equal to 0. Hence, when you integrate, u of xy equal to c is an implicit solution of the equation. Now, what does that mean and how does it help us? Basically, it just helps us to solve all exact ODEs of first order. What you do is you find a u by integrating by using MA108 methods. Basically, u is the gradient function for the vector field m comma n comma 0. So, what you do, if that might sound like gibberish to you, just basically integrate m of xy with respect to dx, basically partial integration, and add a constant, but the constant is constant in y, because if you differentiate it with respect to x, the y term will go to 0. So then we find out that the constant is k of y, which is some function of y. Then you get the u of x and you differentiate it partially with respect to y and equate it with n of xy according to the definition. And hence you would get a very easy to solve and easy to find k of y after integrating, and then you get u. After you find u, you can easily equate it to c, and your work is done. So let us take one very simple example. Y cos x plus 2x e raised to y plus sin x plus x square e power y minus 1 into y dash equal to 0. So how do we solve this? Basically, we just integrate it with respect to x, and since we are integrating with respect to x, the y terms are basically constant. Cos x integration is sin x, and 2x is integration x square, and then we add a k of y. Then we differentiate it with respect to y. Now, since we're differentiating with respect to y, the x terms become constant, and vice versa. And now we would just get that k dash of y is minus 1 and k of y will be minus y. Now you might say it could be minus y plus c, but it doesn't matter since the c is getting consumed anyway in u of xy equal to c. And this is an implicit solution to the given DE. Now you might have various questions in your mind, that are there more solutions and are this the only solution, but that we will talk about a little later.
Now we know how to solve an exact differential equation, but how do we know that a differential equation is exact without trying to solve it? There is a way to do that, and for that we need to first look at closed differential forms. A differential equation is a closed differential form if the partial derivative with respect to y of the coefficient of dx equals the partial derivative with respect to x of the coefficient of dy. So if you have m of x comma y plus n of x comma y into the first derivative of y equaling 0, then m's partial derivative with respect to y should equal n's partial derivative with respect to x. Be careful about whose partial derivative is to be taken with respect to whom. You can remember it like this, that it's sort of the opposite. So m is the coefficient of dx, so take the partial derivative with respect to dy. Just reverse. Now we'll see on the next slide how closed and exact differential forms are related.
So now you know about closed form. Let us talk about theorems on closed forms. So basically there's this one main theorem about exact and closed forms. Exact differential forms are always closed, but closed differential forms are exact only on convex domains. Now, this is useful because you can check for closed forms very easily and then solve, because they would conclude to be exact after checking the domain. Now what do you mean by convex regions is that if there are 2 points in the domain and you connect them with a straight line, the entire line should also lie in the domain. So you can basically imagine a circle. It's basically the same MA108 logic, that the domain must not have holes or should not have a pointed edge pointing inwards, or basically not an angle of the tangent which should be greater than probably 180 degrees. So now that is gone, we could just check for closed and then we could just basically solve it. And how do you check for closed? Closed is basically my equal to nx, where by mixed partials theorem in MA111, mxy dx plus nxy dy is closed. Recall from MA111 that it is same as the proof curl of gradient is 0. Now this is only true for certain domains and certain functions, but in this course this is going to be mostly true. So then what we got to do is basically check whether our thing is closed and then conclude that it is exact because of the domain, and then find the exact function u of x as the gradient, and then conclude that it equal to c is an implicit solution. So as you can also see, I had talked about in one of the slides that u is the gradient of the vector field m comma n comma 0, and as you can see, the curl of the vector field m comma n comma 0 comes out to be nx minus my, which comes out to be 0 because of the theorem of mixed partials, and hence this is how you conclude that a closed differential equation is exact on convex domains, and then you can easily find what the solutions are. And hence after this we'll be discussing a few exercises, and we'll also be talking about domains. So over to you.
Now let's look at a few practice questions. So check if these are closed forms, and if they are, then solve them using the method to solve exact differential equations. I will solve the first and second one here. So m in this equation is y cos x plus 2 into x into e power y. So m isn't the coefficient of the first derivative of y. In a way, it's the coefficient of dx if we multiply the equation by dx. So we will take the partial derivative of m with respect to y. So y cos x becomes cos x. 2 into x into e power y, because e power y's partial derivative with respect to y is just e power y. So we get cos x plus 2x e power y. Now let's look at the other part, n, which is the coefficient of the derivative of y. We'll take its partial derivative with respect to x. So sin x becomes cos x, and x square into e power y. The e power y is just a function of y, so it's like a constant coefficient, and x square's derivative with respect to x is 2x. So we get cos x plus 2x e power y, and minus 1's derivative with respect to x is just 0, so we get cos x plus 2x e power y. You'll notice that this is the same as the partial derivative of m with respect to y. Hence this differential equation is a closed form. Now you notice this is the same example as from the exact ODE slide where we actually solved this differential equation, so you can just refer to that. Now let's move on to the second equation. Here m is x into x square plus y square because that is the coefficient of dx, and n is x square into y because that is the coefficient of dy. The partial derivative of m with respect to y will be 2xy because x cubed plus xy squared, so x cubed is just constant and x comes out like a constant coefficient. The derivative of y squared is 2y, so we get 2 into x into y. Now the partial derivative of n with respect to x, we have x squared into y. Y is like a constant in a partial derivative with respect to x, so that comes out x. The derivative of x squared is 2x, so we again get 2 into x into y. This is the same as the partial derivative of m with respect to y. Hence this equation is also in a closed form. Now m and n are continuous for all real values of x and y. Hence this closed form differential equation is exact for all real values of x and y. So yes, it is exact. Now let's solve it. So if there exists some u whose partial derivative with respect to x is m, then u equals integral of m with respect to x plus some ky, right? M is x cubed plus x into y squared. The integral of that with respect to x will give us x power 4 by 4 plus x square y square by 2, right? Treating y as a constant, and plus ky. Now we also know that the partial derivative of u with respect to y is n. Those are the conditions for u, right? So let's take the partial derivative of u with respect to y and equate that to n. N is x squared into y, and we got u as x power 4 by 4 plus x square into y square by 2 plus ky. So x power 4 by 4 is just in x, so that's a constant with respect to y, and the derivative is 0. Plus x square into y square by 2, we get the 2's cancel and we get y into x square, plus we get the first derivative of k with respect to y, k dash y. Now x square y cancels from both sides of the equation, so we get k dash y equaling 0. This means that k of y is a constant, and we'll just take it 0 because in the end we are going to write u equal to c as the solution anyway, so even if we take some other value of k, it's a constant, so it will get absorbed into that c. So with ky equal to 0, we get u equal to x4 by 4 plus x square y square by 2, and we equate this to a constant to get our solution, x power 4 by 4 plus x square y square by 2 equaling c. That is the solution of this differential equation, the general solution, of course. Try to solve the other two differential equations yourself. First check if they are closed and then solve them using the method for exact differential equations.